Fatigue, variously defined as exhausting the strength or power of recovery. The deterioration of a material under repeated loading. And in the structural sense, the formation of a crack or cracks as a result of the repeated application of loads, each of which is insufficient by itself to cause normal static failure. Not one loading cycle, not 100 or a few thousand, but possibly millions and millions during the life of the structure. Examples exist throughout engineering. Structures large and small, dynamic and static. They all endure fatigue loading, and as such, have a fatigue life. We can examine fatigue cracking safely in controlled laboratory conditions. Take this beam, for instance, a model box girder in a 4-point bending test. The test machine applies a preset load once every 5 seconds. Now, although the stress developed is easily within the elastic range of the material, and the load sustained safely, repetition of the stress ultimately leads to cracking, often at welded joints. Because they appear after repeated loading, they're known as fatigue cracks. Excavator components are largely welded fabrications. Parts are tacked together, then fully welded using MIG or submerged arc welding. In service, they're subjected to a heavy load every time the bucket digs into the ground, which, as we see, is pretty frequently. So the component's design, welding and inspection must reflect this fatigue loading. Small portable parts can be tested in the severest conditions in the lab. But if the job is large and in full-time service, like a bridge support, a pipeline or an aircraft wing, then that's impossible. We need information at the design stage to predict the likely fatigue, wear and corrosion behavior of the structure. And we can gather this by laboratory tests of individual welded joints. Here we use a flat plate in simple tension with attachments on either side. The longitudinal fillet welds contribute little, but we'll see they pose a significant threat to the fatigue life of the specimen. But first, a simple tensile test. Elastic deformation is followed by plastic deformation. Necking becomes evident and ductile rupture occurs at a load corresponding to the material's tensile strength. It leaves a characteristically irregular fracture surface. Now, contrast this with a similar specimen in a fatigue test. A cyclic tensile stress is applied hydraulically. Eventually, it causes fatigue cracking, just here at the end of the weld. But the crucial thing is that this has happened at a stress well below the elastic limit. Here, fatigue cracking appears at the weld toe because of the local stress concentrations and also small weld imperfections. We can clearly watch a fatigue crack growing by testing this aluminium plate specimen in a fatigue test machine. By compressing time, we can speed up the view of crack growth. The test piece has an artificial stress concentration so that the crack is located accurately. By polishing the surface, we can see the crack propagate. First 10 millimeters, then 30 millimeters, to final failure. So, in service, it's important to inspect for evidence of fatigue early in a structure's life, close to load-carrying members where the cross-section changes abruptly. Of course, rust, dirt or paint can make this site job a tough and onerous one. If it's not spotted, a crack will grow progressively until the remaining cross-section can no longer support the force applied, and rapid ductile or brittle fracture occurs. Fatigue crack surfaces have a distinct look about them, a smooth appearance around the point of initiation, and well-defined steps corresponding to the last few cycles just before fracture. In practice, a degree of redundancy is often present in engineered structures. So, a redistribution of stress takes place, and the propagation of a crack may be slowed down or even halted. There's no danger of collapse, but the structure's stiffness may have deteriorated to an unacceptable level. What tests like this do is give a quantitative result of how many cycles produce a sizable crack. So we can now represent this graphically. Numbers of cycles, n, horizontally, and applied stress range, s, vertically. Log-log scales are used, with the horizontal scale up to 10 million cycles in this case. By testing several specimens at different stress levels, we can create a mean line for fatigue performance. The required life of the joint, expressed as a number of stress cycles, can be related to the allowable stress range for the particular joint. If the stress level is raised, a shorter life must be accepted, or, of course, the joint design changed. Different welded joint designs give different fatigue performances. The design of this lamppost, for instance, includes a stress concentrator, which has created an unpredictable fatigue behavior. So far, we've only looked at tests where the stress cycles are of equal magnitude, what's called constant amplitude loading. Of course, in practice, they're often very different. This bridge carries both heavy trucks and small cars. So, it's only by testing welded joints under variable amplitude loading, typically using a computer-controlled machine, that we can simulate actual service behavior. Fatigue cracks produced under variable load are usually characterized by beach marks, centered around the point of initiation. Fatigue performance in welded structures has provided the focus for several decades of research at TWI, the World Centre for Materials Joining Technology. To learn more, why not contact the experts at www.twi.co.uk, or why not call on 44 if you're outside the UK, 1223 899 000.